All right, guys, so it turned out I had so much fun doing these, I couldn't help myself, so I just did them all. And I'm happy to go over them now, but if you didn't do it yet, either, don't write this down, just sort of watch it and see if you follow, and then do them on your own when you can think of it on your own, okay? Because it's really valuable to be able to do that. All right, so for each of these, I highlighted what I see as what I see going on. So I see a double bond here turning into a triple bond. So I know I have to add something to the double bond. So over here, I drew the double bond, adding stuff that will then turn into the final product. I just put PDT for product because I couldn't fit all the product in there. Okay, so then thinking about how to go from here to here is BR2, and then going from here to the final product is the double elimination. Then you need the water workup step to make sure this hydrogen is on there, okay? For the next one, I see the reactivity going from this carbon. I need to lose the Br, and I need to make a double bond here and then add the Br to this carbon. So I'm moving the reactivity, and usually that involves a bridge of an alkene. Okay, so I'm going to have a terminal bromine, and I'm going to turn it into the internal. So to do that, I need to eliminate using either NaOH or tert butoxide. It doesn't matter because you only have one option for beta hydrogen. It's this hydrogen, so it doesn't matter how you take it off. And then HBr to add Markovnikov. For this one, I'm changing the double bond from here to here, so I need to change the reactivity to add something here. So I need to do Markovnikov addition of, let's say, HBr, and then you want to do elimination to make a Zaitsev. So don't use potassium tert butoxide, use a small base like sodium hydroxide or methoxide or ethoxide. This one you're starting with an alkane. So the only reaction you have is Br2, radical halogenation, or NBS sometimes is used, and with heat or light initiating that. Once we get the alkyl halide on there, now we can eliminate it Zaitsev, or you could have eliminated it Hoffman as well. It's another possible question you could have. So then you would use tert butoxide for that. For this one, it's a little tricky because you have alcohol, which is not a good leaving group. We need to eliminate it though, and then add an OH group, Markovnikov. So to do that, I'm thinking, even though it's not ideal, you want to have a tertiary in order to do E1. This is secondary, so it's not so bad, but there's a better way to do this that you'll learn in a future chapter. So just for now, though, let's say you do E1 elimination, which is H3O plus and heat, and then you make the alkene here, and then you add Markovnikov with acid catalyzed hydration, or HGOAC2, oxymercuration, demercuration, but there's no possible rearrangement, so you could use acid catalyzed water is fine. And then for this last step is changing the Br from here to an OH group here. So we need to bridge that with an alkene and then add Markovnikov, an OH group. So we can just use, we got to use a small base. Don't use tert butoxide or else you'll get the double bond on the end. And then add OH Markovnikov with the same reaction we did here, acid catalyzed water. Okay, and now let's do some practice with the retrosynthetic approach because this is very useful. Okay, so it might be a little painful at the beginning, but the more synthesis you'll do, the more you'll appreciate this. So I'm counting these carbons, 1, 2, 3, 4, 5. Okay, and I think it comes from these. Okay, so you can tell that you're going to have some group, an ethyl group being added on. So the retrosynthetic approach is identifying your synthons. Synthons are the pieces that you glue together. Synthon. Okay, so to do that, I think you see that this is an alkylation reaction. So, this, when we do retrosynthesis, we use this special back arrow that this came from this plus something like this. Okay, and so that's our retrosynthesis. Okay, so now going forwards, what is it that we need? So we need two carbon group with some kind of reactive site like an alkyl halide. That's going to make this one attack here and release there. So that's why it helps to know mechanism pretty well. So what we need to do is first make this reactive. I need this to be negatively charged, and then I have my positive part here with the alkyl halide, and there's my glue. Okay, negative and positive will come together. So to do that, I need to make this negative by using a strong base, NaNH2, and then I will have my ethyl halide, let's call it a bromide, and that's how we figure it out. So retrosynthesis means just thinking backwards. What are the pieces that are missing that you had to add on to this? It must have been something like this, and then try to determine what the glue is. What's going to make which part is negative and which part is positive, and that should help you think about what the reagents need to be. Why don't you guys try this one? Okay, just sort of analyze it, figure out which carbons are which, and then find out are there any missing carbons or what reagents can help us here. So retrosynthetically, think about what do we need to work backwards to in order to end up with this. All right, so what I see, you guys, is that this ring obviously is here, and I have one carbon off of it. So this is my group that's missing, is this. And now we know that with an alkyne, we can add any kind of group onto it by having an R group with an alkyl halide here, okay, because that's my positive. So hopefully you guys saw that. So what I need to do then is add this group, since I already have this right here, okay? So how do I add this group? All right. Usually you see it the other way, where we start with the alkyne and then we add this alkyl halide as a reagent. Well, all you have to do, I think you're going to love this, all you have to do is write this reagent, and you can even write it negatively charged already with a counter ion. So let's say it's sodium acetylide. Okay, so that's sort of neat. You can just write it like that. All right. All right, so here we're going to use a retrosynthetic approach again. So I see that this triple bond is this triple bond, right? So I need to add these other groups onto there. So to make that a glue, I need this to be negative, so I'm going to use NaNH2. And then I need to use something with a methyl group, so CH3Br. And then I need the other side to react, so I'm going to use NaNH2 again, sodium amide, and then I'm going to have an ethyl group, so ETBr. All right. So, and how did I come up with that? I just looked at this and I said, oh, these are my new groups, so I need to have reagents with those groups on them. Sorry, this ETBr. Okay. Sorry, that's not clear. ethyl bromide. All right, CH3CH2Br. Okay, so go ahead and give these a try. See if you can figure out what those synthons are and how to tie them together and come up with your list of reagents. All right, guys, so here's what I have is a 2-carbon unit here with a triple bond, so that's my reagent, okay? And I know that a negative charge there is going to attack here and let that go, so I can just show it in its sodium salt form. For this one, it's the cleavage here, right? So this was oxidative cleavage, so I inserted an oxygen where I cleaved. So here's where that cleavage must have occurred. So I use ozone and then either DMS, dimethyl sulfide, which Klein uses a lot, or zinc in water, which you often see as well. So now, more practice, okay? So let's do one together. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5. So this is the cleavage point, but instead of an alkyne, I had an alkene. And notice it's cis, so I probably had an alkene, and then my last step was to reduce it to a cis alkene, an alkyne to a cis alkene. Okay, so let's see if we can figure that out. So first, we know we can add this chain. If it's an alkyne, we just need to make it into a negative charge first. So that's why we use NaNH2. And then we're going to add our R group, which has to have 3 carbons and an alkyl halide. 1, 2, 3. So this is going to be a propyl, and then I can call it propyl bromide, PRBr, or CH3, CH2, CH2Br. Okay, or you can just draw it out if you want to. All right, and then at that point, I'm going to have a triple bond here. So I need to make it into a cis alkene. So I'm going to use H2 and Lindlar's catalyst. And that's going to make this into cis. All right, so that's now adding multiple things. Whereas before we were just adding R groups and doing alkylation, now we're also changing the functional group from an alkyne to an alkene. So these problems are getting a little bit more complicated already. Okay, so go ahead and give these a try with that in mind, that you might have to lengthen or shorten the chain and do additional steps to it. But think back to retrosynthesis and see if you can figure out what pieces you're adding together or how you're moving the functional group. Where's the functional group currently, and how are you moving it? Do you need to make alkenes along the way? All right, guys, for this one, a little bit tougher. Okay, so I'm highlighting all of these, and I noticed that I ran out of reactivity. So this is just an alkane chain. So not quite sure how we're going to get this group on there, but I do know that there's a cleavage point there, or synthon attachment there. Okay, so just thinking about what I can do, I do definitely want something reactive on this end so that I can eventually connect it with these 2 carbons. So I'm thinking maybe a double bond and then react one thing there. And then it occurred to me, oh, that I could add an alkyne to an alkyl halide. So basically just make this chain into an alkyl halide on the end and then add your alkyne through alkylation. So to do that, we're going to reduce to an alkene. That way we only have one Br. We don't need multiple Brs. So H2 Lindlar or sodium and ammonia is fine. HBr in peroxide to make sure that the end carbon is the one with the bromine. We don't want Markovnikov in this case because we need this to add on at the end, okay, on this carbon here. Then I need to just add my acetylene, which is a negative ion, acetylide ion. It's a sodium salt. Okay, all right. For this one here, I noticed that I've got this reactivity, and then we've got to have a cleavage here. Okay, so I need to cleave that off eventually. So I'm thinking a double bond or triple bond and then cleaving it. Now, some of you know from a double bond, I can cleave this. So first I have to eliminate the BRs, and I can either, I can do that to make a triple bond, and then I could cleave a triple bond and then use ozone, and then I'll get a carboxylic acid, and I'll get 1 carbon unit, that's CO2. Or I could add some steps and turn this into a double bond and then cleave the double bond using hot KMNO4. But that adds steps, so it's not really necessary. So using our knowledge of alkyne reactions, just cleave it with ozone there. For this last one, I recognize that the carbons that need to be added is right here. All these carbons are already in the starting material. Again, I'm thinking back to what I did up here. In order to add reactive groups on the end, I'm thinking this was a triple bond reduced to a double bond. This must have added on this carbon here, so I do anti-Markovnikov again, and then add this group as a triple bond negative ion propyne ion, 1, 2, 3, 4, sorry, butylide ion with sodium salt. And this is trans, so I need to take that triple bond. What I make after this is the triple bond form, right? So I've got this like that, and then I need to make the transalkene. So I use sodium in liquid ammonia for that part. I think these are a duplicate of what we just went over, and then I added a few more problems from the book here, so you guys can do that when you want to, if you have some time. For this problem, all the reagents are provided. Let's walk through this step by step and see. Oh, 8 steps. All right, it's sort of fun, but because you got to know how it builds on each other, so that's great. But synthetically, it's not really great to have so many steps. But anyway, let's work through this one. So after the first step, we're going to do anti-Markovnikov HBr addition. So I'm going to have a Br here. And then I'm going to do a terp butoxide. I'm going to do a terminal alkyne or alkene here. Okay, so now I want you guys to go through and give me the rest of these. Okay, so show me what happens after step 3, 4, 5, 6, 7, and then how do I get to this finally? And then let's check our answers with each other. All right, guys, so after all those steps, I get Br2 addition trans, but this is, can't really tell because it rotates. Then you have a triple bond from double elimination, steps 4 and 5. And then step 6 is to do the alkylation here. And notice, sort of redundant, you could just get rid of these 2 steps. And excess NaNH2, sodium amide, means that it's going to automatically be negatively charged here. So that's perfect, actually. We don't want to neutralize that yet. You said just throw in methyl iodide. You get this methyl group on here. And now you've got your 3-carbon chain that you need, and you just need the alkyne to be reduced to a transalkene. So make sure you use sodium in liquid ammonia rather than H2 Lindlar. All right, so now that we can see an example of reactions with lots of steps, okay, now let's try some of them on our own. Okay, so let's do A together. I know that this triple bond here is my reactive site and it has to be corresponding to there. So I'm going to need to add 2 carbons onto one side of this and then have a double bond that makes my halohydrin from Br2 in water. Okay, so that's going to look like this. First, I want to have NaNH2 to have this side negative, and then I want to react it with a 2-carbon group, so ethyl iodine, let's say. Okay, and then step 3 is I'm going to need this to then turn into some form of alkene, and then I can do my Br2 in water and get this halohydrin. Okay, so it doesn't matter if it's cis or trans alkene here, so I can use H2 Lindlar, and then I can do my Br2 in water will give me Markovnikov addition of the OH group. Okay, so it's a Br bromonium ion. If you remember that mechanism, it goes into a bromonium ion like this, and then water attacks the more substituted and breaks that ring open. Okay, so that's how I get my halohydrin. Sorry, it's a bit messy here, but that's how that works if you recall. Okay. All right, so we've got some different things going on here. Oh, epoxide. Okay, so maybe MCPBA from a double bond might be used there. And right here, oh, this looks tricky too. Obviously, this part is here. So we've got something going on here. Okay, so see if you can figure that out. Just think about, oh, that's a geminal dihalide. What can I do with that? And where does a carbonyl come from? It can come from an alkyne. It can come from OH oxidation, but technically that's in a future chapter. It's probably an alkyne. Can you get a ketone from that? I think we learned that. So give those a practice and check your answers, and I'll post them. And that's it. This is sort of a long chapter, but lots of practice. Go through it multiple times till you feel comfortable with it. All right. Good luck, everybody.